G'day YouTube, welcome to my channel. It is Wednesday the 9th of March 2023. I'm in my Radio Shack and today we will be showing you how to decrypt a GSM data capture file. I need to preface this with the following. This video is being made for educational and experimentation purposes only. IMSI catching, SMS sniffing and voice call interception on cellular networks is illegal and punishable by hefty fines and imprisonment. Here is the legislation of Australia prohibiting interception of private telecommunications. And here is the penalties for the offence. Australia has no active GSM networks due to our 2G sunset back in 2016, so I couldn't intercept these communications even if I wanted to. This is probably going to be quite a long video. I've done little to no preparation for this, and I intend to show from start to finish a potential workflow on how to obtain the KC value and decrypt some GSM traffic in real time. There's going to be quite a lot of copying and pasting data between Windows terminals and text documents, so be warned that it might not be very entertaining to watch. The encrypted data capture file isn't that interesting either, but I won't spoil the surprise and we'll analyze the data after we've decrypted it towards the end of the video. A lot of my commands are pre-typed just for copying and pasting into the terminal because I'm a notoriously slow typer. So just pause the video if you need to transcribe them, but normally I try and put the commands I run in the description for easy copying and pasting for you guys if they fit. So here we go. So the required tools you're going to need is Dragon OS LTS Public Beta 2. It's a pre-made image built on Ubuntu 18.04. GNU Radio 3.7 is pre-installed and working. Virtual machine or bare metal on a bootable USB are both acceptable ways to run this operating system. You only need to use this, I guess, if you are going to replicate my setup, but you could be using Kali or any of those other pen testing Linux distributions. And while we're on the topic of Dragon OS, go and check out Aaron over at CMA Executor YouTube channel. He's the author of Dragon OS, and he doesn't get anywhere near enough recognition for his amazing channel and incredible operating system. The next thing you're going to need is AIRPROBE patched for GNU Radio 3.7. This is used for decoding the GSM capture file and printing the frame bursts required for cracking. We're going to talk about frames later and bursts. Later versions of GRGSM decode can print frame bursts with the P argument, but I couldn't get GRGSM decode to read this particular capture file. Next thing you're going to need is Wireshark. It's included in Dragon OS already, and it is required for decoding and analyzing GSM packet data. The fourth thing you're going to need is Kraken with a hard drive with the rainbow tables written to it. This is used for cracking the A51 keystream and ultimately finding the KC value used for decryption. This is a mammoth task setting this up by itself, and it probably requires a dedicated tutorial, but that's beyond the scope of this video. Just remember, if you're using the Crazy Danish Hackers YouTube tutorial for installing Kraken, you need two separate hard drives. The source drive contains the downloaded DLT files, and the target drive will have the DLTs written to it in a raw format. He doesn't explain that clearly enough in his video. Many followers of his YouTube tutorial reported losing their 1.5 terabytes of downloaded DLT files because they tried to write them in raw format to the same drive where the DLT files were kept. This happened to me 2 times, and you scroll through the comments of this video and there's heaps and heaps of people complaining about that issue. So you need 2 hard drives to set up Kraken, okay? Next thing we need is a capture file. A capture file is in C file format. It is basically a computer transcribed version of GSM waves traveling through the air captured by a software defined radio. This capture file was uploaded with permission by the owner of the data for use as a decoding example for AIRPROBE. Do not ever attempt to crack private GSM communications from any other mobile subscriber except yourself. Only crack your own GSM communications. You can find voice call, SMS, and GPRS data traffic coming from your own telephone by obtaining the TMSI value from your SIM card, which is the temporary mobile subscriber identity, and cross-referencing that with decoded packets in Wireshark. As far as I'm aware, this file has never been publicly cracked, and that is evident by this person asking for the key in the GSM Google groups. So doing a public first here potentially. So let's get to it. So what we're going to need to do first is open Wireshark. And then we go into another terminal window. And we need to utilize AIRPROBE to decode the BCCH, which stands for Broadcast Control Channel, on time slot 0. And now we can see the top window pane of Wireshark populating with decoded packets. So what we need to do is sort the packets by alphabetical order, locate the immediate assignment packet, drop this menu down, GSM CCH, immediate assignment, click channel description, and we can see that there's been an allocation to an SD CCH8 channel on time slot 1. So we'll restart the Wireshark capture, and we'll utilize AIRPROBE again to decode the SD CCH on time slot 1 and also print the bursts to a text document. Talk more about bursts very shortly. So we just run that command. So we locate the ciphering mode command, drop this drop down menu down, click on cipher mode setting, and just confirm that A51 encryption is in use. Kraken can only crack A51 as far as I'm aware. So if it's A53, don't even bother. And A50 means that there's no encryption being used. So be very, very careful when you're decoding that traffic. So all the data beyond this ciphering mode command packet is encrypted, and it's not decodable by Wireshark anymore. So we can't go further than this. To see what traffic exists beyond this ciphering mode command packet, we need to find the KC value that the base station provided this telephone to secure the communication. So in this top pane of Wireshark, these are the data link layer protocol packets. Each packet corresponds to a frame number, which can be found in the bottom window of Wireshark under GSM tap header. Each GSM frame is made up of 8 bursts, which are the raw ones and zeros of a transmission. We can extract these bursts with AIRPROBE as they are required for cracking A51. So our target packet is going to be a LAP-DM function UI packet. These are an idle packet that are repeated every 102 frames on this particular GSM base station. A lot of carriers utilize different equipment and implement the GSM standard differently, but this particular GSM base station repeats LAP-DM function UI frames every 102 frames. And we can confirm that by locating frame number 1670814, copying that value, opening up your calculator, pasting that value, and then adding 102. And we can see that 1670916 should be the next lapdm function UI packet. So we'll click the next target packet, and we see that 1670917 is the matching frame. So that is just a confirmation that this base station is transmitting these frames every 102 frames. So what we're going to do is we're going to copy that value and then paste it into our working text document under target unencrypted frame number. So now that we have our target packet, we need to guess where the next lapdm function UI packet is in the encrypted form. So that packet exists after this ciphering mode command in encrypted form somewhere. For a more in-depth explanation on the guessing phase of cracking, please refer to my previous GSM cracking video from last week. Because we know that lapdm function UI packets are repeated every 102 frames on this GSM base station, we can use a calculator to add 102 to the frame number of the target packet. So we'll copy this value, paste it into calculator, and then we add 102. So this frame could potentially be the encrypted form of a lapdm function UI packet. So what we'll do is we'll copy that value and paste it into our working text document under guessed encrypted lapdm function UI frame number. So the next thing we need to do, we don't need Wireshark for a while now, so we'll just put that into the background and go to our AIRPROBE working directory where our capture file exists and locate the burst.txt file. In order to use Kraken to find the KC value, we need to generate a pure A51 keystream to feed into the Cracker utility. This keystream can be generated by XORing the frame bursts together from the unencrypted target frame and the encrypted, the guessed encrypted frame. So yeah, as we can see that AIRPROBE outputted this file when we ran the command decoding the SDCCH. And then what we'll do is we'll use the find utility and we'll find the 12 lines of GSM bursts that define this packet. So we hit find there, and we need to copy all the frames from 913 last 3 digits to 916 last 3 digits. It'll be a total of 12 lines. So we copy all those, paste them into the target unencrypted frame burst section of our working text document. And then nextly, we need to find the guessed encrypted frame and copy the 12 lines of bursts relating to that packet. Use Control F find utility. Paste that, ignore this. Do not copy anything here. Scroll down a little bit and we need to copy the 12 line. We need to copy all these bursts, 12 lines from 015, last 3 digits, 016, 017 and 018. Again, it'll be 12 lines. So we just copy that, paste it into the guessed encrypted frame burst section of our working text document. There's a lot of there's a lot of data in our text document now. We can close burst.txt. We don't need that anymore. So we've got a lot of data in our text document. So we can remove the irrelevant bursts that serve no purpose to cracking on both the unencrypted target frame and the guessed encrypted frame. So because I cracked this capture file in the past, I know which bursts deliver results. So to save some time, we will only XOR the burst required for the cracking. So remove all the bursts that don't start with the letter P. If they start with S and C, delete them. So we're reaching the boring phase of the tutorial now. Just go ahead and delete the lines that are irrelevant to the cracking. And do the same for the guessed encrypted frame bursts. Only keep the lines that start with P. If this were like a regular workflow, you would XOR all the bursts with each other. But because I already cracked this file yesterday, I know which bursts deliver results. So to speed up this video, we will just keep the relevant frames that we need for obtaining the KC. Okay, so now we need to open another terminal. So what we need to do now is we need to utilize Kraken's XOR.py utility. So you don't need to compile this. This is just a Python script that you can just download from Git. So yeah, you just cd into the directory and then run your XOR.py script, and we need to feed that script the first burst of the target unencrypted frame, and also with a space, and then the first guessed encrypted frame. Like so, hit enter, and then we need to, this is the output. So this is the XOR result from this burst and that burst. So we'll just paste this down here. And then you do the same for the rest. So again, very boring. You know, people generally write automation tools for this phase, like the guessing, the XORing, and oh, I think I did that incorrectly, sorry. Oh yeah, people write automated tools. Some of the tools that automate this step are Pytical, Top GUI, AutoKraken. I think there's one called GSM TK is another one. But writing such a tool to automate the guessing, the XORing, and the feeding of Kraken is far beyond my coding ability, unfortunately. But people do write their own Kraken, guessing automation tools. And neglect to share them with the community because it's pretty illegal to do so. So there we have it. That's our XOR output from XORing each burst, each unencrypted burst with an encrypted burst. And I'm just going to take a moment to just double check that I have the correct burst, because I was running into a problem earlier where I was having to re-record the video when I got to this step about 4 times so far. So yeah, I'm just quickly double checking that everything is okay. I'm assuming it was something to do with VNC not copying and pasting correctly, but it seems to have worked this time, so we'll move on. So out of these 4 XORed bursts, one of these is a crackable A51 key stream. So far, so good. Let's keep moving on. So now what we need to do is I need to log into my private Kraken server, which is sitting over there on a table relative to me. It's powered on. I'm already logged into SSH. I've CD'd into the Kraken directory, and then I need to run this command. So what Kraken is doing now is it's loading the rainbow tables using an index file. Index file contains all the addresses required for Kraken to access the rainbow tables, because the rainbow tables are written in raw partition. You can't actually browse it with a file manager, so it's a really efficient way of keeping large amounts of data. And while that's doing that, I'll have a sip of beer. So yeah, Kraken's got a really, really easy user interface. It's only got 3 commands: crack, test, and quit. So we will type crack into it. We can only crack 1 burst at a time. So yeah, it can sometimes be quite time consuming. This Kraken machine is very old and slow. So because I know which XORed burst delivers results, we will go ahead and crack the 3rd XORed burst. I'll just quickly label these so we can differentiate, and I can refer to them by this name from now on. So yeah, as I said before, I know which burst delivers results, so we're going to go ahead and I'm going to copy the 3rd XORed burst, type crack, space, and then paste that potential A51 crackable keystream, and then hit enter. So yeah, this computer is a dual core Core i3 with a H61 motherboard in it, which is from the era of about 2011. So it's not really a number crunching beast, unfortunately, but it gets the job done. So fingers crossed, we should get some results very shortly. Bingo. Yeah, Kraken has found a candidate key, which is this string of numbers and letters at position 11, which I believe it means maybe 11 bits into this string, this burst. It has found a candidate key at position 11, bit position, on attempt number 0. And the rainbow table was number 212 that it's found this result. So we'll just Control C out of that, because I know it won't spit out any more results. Sometimes it spits out multiple results, but this particular one, just the one result. So yeah, we'll copy that and paste it into the Kraken output section of our working text document. So yeah, the next stage is we need to find the previous burst. Because the candidate key Kraken found in its rainbow tables is not the KC value, we need to utilize another Kraken binary called find KC to finally generate the actual KC value. So to do this, we need to generate some input to feed to the find KC utility. So we need to locate the previous burst before like the previous burst before the one that we cracked, right? So 1670914. So we need to open up our, oh no, we just go scroll back up. So we need to copy this line here, because the reason we're doing this is because we need some of these numbers later on to generate the input to feed KC. So that's the previous burst, because we know the 3rd result, the 3rd burst gave results. So the previous one is this one here of the unencrypted target frame. So we'll just paste this down to here into previous unencrypted burst. Oh, frame, sorry. Oh yeah, burst, sorry, yeah. And then do the same for the guessed encrypted burst. So we know the third burst gave results, so we copy the burst before that, and we'll do the same. We'll paste it down here. So yeah, we need some of these numbers to find KC, so that's why we're just jotting them down in a little bit more accessible area of our text document. And then we need to copy the second XORed burst, which is the burst before the burst that gave us results. So we'll just copy that from there. We don't need to use the utility again because we've already got the output there in the text document already. So yeah, we'll just save that because we're getting quite a lot of juicy data in our text document now, which is going to help us find the KC. So, okay, this is it. Lo and behold, the final step of the tutorial. So we need to utilize find KC binary to find the KC value now. So this one's a little bit tricky, so you have to follow along with me. I'll try and explain it the best I can. Again, not a computer scientist or a cryptology expert here. Okay, so we need to go to our text document. And we need to copy the candidate key, which is that string of numbers and then one letter after it. And then we first we need a CD into the utilities directory of Kraken. My apologies. Sorry about that. So we'll utilize, we'll go back to this window, sorry. Yep. And then we'll just double check that the binary's in there. Yep, find KC, that's the utility that we will be utilizing. So we need to copy this candidate key. First we have to write find underscore KC. / find KC space, and then we copy the candidate key, put another space, type the bit position, which was position 11. Thirdly, we need to copy the guessed encrypted burst's frame count into the terminal. So 567 is the last 3 digits of that. Five, six, seven, sorry. 567. So we 2580567. And then we paste that there. Fourthly, we need to copy the previous guessed encrypted burst frame count into the terminal. So that is 2580534. So these are called frame counts, these numbers here. This is the frame number and this is the frame count. And it's used for mixing into A51 while it does the back clocking, I believe. So we paste that there. And then finally, and finish the command, we will send to find KC, copy the previous burst XOR output. So previous burst XOR output field from down here, copy that, space, and paste that right there. So here's the moment we've all been waiting for. Will I have to record my video again or not? Stick around and find out. We'll press enter on that. And success. There we have it. That is what we've spent almost 30 minutes trying to achieve. The find KC utility has found 8 candidate KC values, and the 8th one is the decryption key that we can feed into AIRPROBE and reveal the encrypted GSM traffic. So yeah, we'll copy that result to our text document. And we'll just have to do some reformatting so we can feed this value to AIRPROBE and then see what decrypted traffic was hiding behind the cipher mode command. Spoiler alert, it's not very exciting, but it's still pretty fun to do this kind of stuff anyway. So yeah, this is the final stage of the tutorial now. We're going to go back to our AIRPROBE window, terminal window, sorry. And we're going to paste the command for decoding the SDCCH on time slot 1 again, except we're going to do it differently this time. We're going to put a space after it, and we're going to copy the KC value that we just cracked into it. And then we're going to go to Wireshark, restart the capture. And yeah, just like I alluded to previously, the encrypted packets are not that interesting. It appears, well, I'll just run the command first. Oh. Here we go. So I'm not sure if this has been publicly released before, but this could potentially be the first time that these packets are being displayed on the internet. So that's pretty cool. Just like I alluded to previously, the encrypted packets aren't that interesting. It appears to be traffic related to LAI, which stands for Local Area Identification, and the LAC where is it? The LAC stands for Location Area Code. So this information was probably encrypted for the purpose of protecting a mobile subscriber's location as they move between base stations, cell towers, and coverage areas. Typical tracking prevention type stuff on cellular networks. So yeah, it kind of makes sense that this, you know, information that could potentially be used for tracking a mobile user is being encrypted. So yeah, that's very, very cool. I'm quite happy that I achieved to crack real GSM communications. It's taken me a long time, like months and months and months of reading and gathering tools and things of that nature to achieve such a thing. So as far as I'm aware, the decryption key of this capture file has never been publicly disclosed. So here we are. It's all yours, community. I should reiterate to any law enforcement watching that this GSM capture file was recorded and uploaded by the owner of the data themselves for the purpose of educating 2G GSM users that their communications are potentially insecure and open to eavesdropping if they use these systems. So yeah, like usual, I'll upload a zip archive of the capture file, my cracking notes, document, and anything else related to this video, and then I'll upload it to Google Drive and put the link down there. So what's next for my GSM hacking adventures? Nothing at all. I achieved what I set out to do by cracking actual GSM communications in real time, and in the process I educated some viewers that may be interested in cellular security and potentially inspired them. I intend to dismantle this GSM cracking setup and delete all the virtual machines and all the bootable USBs relating to it. I may potentially sell my Kraken hard drive along with the IDX and config files to someone if they're interested, but that's a big maybe because I might repurpose the hard drive for something else. It's a 1.5 terabyte. Oh, sorry, it's a 3.5 terabyte NAS drive, so only 5,400 RPM, so not very good for cryptography stuff. But yeah, everything else is fairly well documented on my YouTube channel now if someone wanted to replicate these steps. So yeah, it's time for disclaimers now, like usual. So yeah, this video was made for the purposes of education and experimentation purposes only. IMSI catching, SMS sniffing, and voice call interception on cellular networks is illegal and punishable by hefty fines and imprisonment. If you value your freedom and don't want to go to prison, do not ever, ever replicate the steps in this video to eavesdrop on private encrypted telecommunications. Okay, you have been warned. Thanks very much for watching, everybody. Bye.